Hi everyone, Maggie back again with part 2 presentation on phosphodiesterase 6. So in case you forgot some of my very compelling video from last month, I just want to take a moment to revisit some key information about my enzyme, which is good old PDE-6. So this is a phosphodiesterase, which means that it cleaves bonds through hydrolysis, and it's critical to the vertebrate perception of light. So consequently, we find it in the retina. PDE-6 allows the brain to perceive light through signal transduction as it regulates levels of a molecule called cGMP, or cyclic guanosine monophosphate, that's located in the photoreceptor cells. Now what's important to note is that this enzyme is cGMP specific. That is going to come up later in this presentation. And also it's super efficient at what it does, and so that means without it, you would not be able to see, and so PDE-6 is kind of a big deal. So when we talk about hydrolysis of cGMP, what does that really look like? So here we have our reaction scheme. We have our cGMP molecule there on the left, and you can see on the left-hand side, we have a cyclic phosphate group. In hydrolysis, the PDE enzyme will facilitate a molecule of water coming in and cleaving a chemical bond through the addition of a hydroxyl group. And you can see where that hydroxyl group comes in on the GMP molecule on the right. It sticks right onto that phosphate. And so now that our GMP molecule has lost its cyclic nature, the visual signal can be transmitted. So I had sort of a hard time finding really specific information about the catalytic mechanism of PDE-6. So I want to back out a little bit and talk about mammalian phosphodiesterases as a whole family of enzymes. We have 11 members that we know of in this family, and they're sorted into 3 groups. We have the CAMP molecule specific group. That would include PDE-4, 7, and 8. We have the cGMP specific group, which is PDE-5, 6, and 9. And then we want to make sure that we're sort of looking at this cGMP specific group, of course, because it contains our enzyme, PDE-6. And the last group is PDEs with dual specificity for both CAMP and cGMP. And that includes all the rest of them, so PDE-1, 2, 3, 10, and 11. As it turns out, all of these phosphodiesterases share a conserved catalytic domain. And what that means is that they have about 270 to 300 amino acids that follow generally the same sequence in all of their sites of catalysis. So pretty cool. They also have sites that are active sites that can be described as having 2 components, a nucleotide recognition pocket and then a hydrolysis center. And obviously, the nucleotide recognition pocket is going to be structured in a certain way for each enzyme to allow in either cGMP or CAMP or both. And all the PDEs have what's referred to as a hydrophobic clamp in the nucleotide recognition pocket, and that's formed by side chains of phenylalanine 456 and leucine 420. So interestingly, researchers believe that all the hydrolysis centers are the same in all phosphodiesterases, so that would lead us to expect that the mechanism of hydrolysis is identical in all of them. A little historical side note, just for context as we continue through our discussion, the first crystal structure of a phosphodiesterase was determined only in 2000, so 20 years ago, using PDE-4B. And since then, only 7 other phosphodiesterase crystal structures have been reported, so we don't have all of them at this point. And unfortunately, PDE-6 is one of those enzymes that has yet to be reported. But I did find a great paper by Liu et al. That discusses the mechanism of PDE-9. And this is fantastic because if you remember, in our 3 groups of phosphodiesterases, we have PDE-5, 6, and 9 are all cGMP specific. So we can reasonably assume that the catalytic mechanism of PDE-9 is going to be similar to PDE-6. So let's keep that in mind as I continue with the next few slides. There are 2 amino acids, histidine 643 and aspartate 754, that are conserved across all the PDEs, and researchers believe strongly that they are the main participants in the catalysis working in the nucleotide recognition pocket. In the diagram above, we can really focus down into that catalytic center. and that's found in all the phosphodiesterases that we discussed before. So with modeling and theoretical calculations, researchers have determined that histidine 252 is the general acid in the hydrolysis reaction. So here is our histidine 252 circled in yellow. We also find 2 metal ions in our hydrolysis center, and those are circled in light blue. And they're denoted in this diagram as M1 and M2, so just want to make sure that's clear. In PDE-9, the cations are manganese and magnesium, and we can also see we have water being flanked by those cations, and that's labeled with a W. So let's look at the reaction now. We start off with that oh so important histidine 252 and our metal cations. And we'll stick in our CGMP molecule. We'll see that the cations are acting as Lewis acids by accepting pairs of electrons from the 2 oxygens attached to the phosphate group, and the water is interacting with the phosphorus as a nucleophile. The histidine 252 is acting as the general acid by donating a proton to the oxygen in that 5-membered ring. Okay, cool. So our hydroxyl group of water joins with the phosphorus, and the oxygen of the ring has accepted the proton from histidine 252, so the ring breaks open when the oxygen bond with phosphorus breaks, and now we have the phosphate group still sharing some electrons with M1 and M2 in this sort of ring-like formation, intermediate, and that's not going to last very long, as the final part of the reaction shows us that histidine 252 goes on to try to react with the negatively charged oxygen in the phosphate group. And there we have it. CGMP is now GMP. So pretty cool. This is all well and good, but how do we really know that this is what's happening experimentally? Well, researchers use a tool called freeze trapping to collect snapshots of enzyme substrate complexes as the reaction progresses. For PDE-9, the enzyme was first crystallized with a low affinity IBMX, and then it's soaked in the CGMP molecule, which has a much higher binding affinity. And so that leads the substrate concentration to be so high that the reaction will reach a kinetic steady state where the reaction intermediates can accumulate. And then those complexes are captured and preserved by rapid freezing with liquid nitrogen and analyzed with mono wavelength X-ray data. I really could go on this topic for quite a while, but as we're at the 10-minute mark, I'm going to wrap things up for this presentation. A couple of points I'd like you to take away. PDE-6 catalyzes the hydrolysis reaction of CGMP to GMP. Phosphodiesterases are a family of 11 members that can be divided into 3 groups, which are the CGMP-specific group, the CAMP-specific group, and the dual CGMP-CAMP-specific group. All PDE active sites contain a nucleotide recognition pocket with a hydrolysis center and 300 amino acid sequence that is conserved across the family. Key players in the chemical reaction include the absolutely conserved histidine 252, which acts as the general acid, 2 metal ions, in the case of PDE-9, they're manganese and magnesium that act as Lewis acids, and water, which provides the nucleophilic attack on the phosphate ring. So the oxygen-phosphate bond is broken through hydrolysis, we get the open ring, and that leads to light perception. So thank you so much for watching. I'm happy to take your questions in class about PDE-6, and it's been really fun to share this with you.